Welcome back. Just like in the last video on nominal variables, we're still working with categorical responses that have more than two categories. But now, the categories come in a natural order. The generalized Logit model treats every category as an unrelated label. That's fine for transport modes, but a satisfaction rating or a cancer stage has a clear ranking, and throwing that ranking away wastes information. These are ordinal responses. Dissatisfied comes before neutral, which comes before satisfied. The catch is that the gaps between the levels aren't necessarily equal, so we can't just treat the rating as a number and run an ordinary regression on it. Instead, we model cumulative probabilities, the chance of landing at or below each level. We'll define the cumulative logit and its cut point parameters, add explanatory variables to get the proportional odds model, and then swap the logit link for a normal one to get the cumulative Probit model. Let's get into it. Ordinal dependent variables are categorical variables that have a natural ordering among the categories, but where the intervals between the categories are not necessarily equal. A good example is customer satisfaction ratings: very dissatisfied, dissatisfied, neutral, satisfied, and very satisfied. Unlike a nominal variable, these clearly follow a logical order. But here's the catch. The difference in satisfaction between neutral and satisfied isn't necessarily the same size as the difference between satisfied and very satisfied. The order is meaningful, the spacing is not measurable. Educational attainment works the same way. High school, bachelor's degree, master's degree, PhD. These follow a clear order, but the jump in education from one level to the next isn't uniform. Because the categories are ordered, we can do something we couldn't do with nominal data. Talk about the probability of being at or below a given level. That's the idea behind cumulative models, which we'll cover next. Cumulative models are useful for understanding how explanatory variables influence the probability of being at or below each category level of an ordinal outcome. The basis of these models is the cumulative probability. For an ordinal variable y with c categories, the cumulative probability of being in category j or lower is just the sum of the individual category probabilities, pi1 through pi_j. Picture the 5 ordered categories laid out as a bar, where each segment's width is that category's probability. The full bar has total probability 1. Choosing a value of j amounts to slicing that bar at 1 point. Everything to the left is the cumulative probability of being at or below category j. Everything to the right is 1 minus that. The cumulative logit is the log of the odds of that split, the probability of being at or below category j, divided by the probability of being above it. Written out in terms of the category probabilities, it's the sum of pi1 through pi_j over the sum of pi_j plus 1 through pi_c. The simplest cumulative logit model just sets that equal to a constant, alpha j. These alphas are called the cut point parameters, and they define the boundaries between the levels of the ordinal response. These parameters are non-decreasing, which ensures alpha 1 is less than or equal to alpha 2, and so on. That reflects the cumulative nature of the distribution function. As j increases, you can only add more probability, never take it away. One caveat worth flagging. The source material notes alpha 1 through alpha c, implying c cut point parameters. But the cumulative logit formula doesn't hold at j equals c because the probability of being at or below the top category is always 1, and the log odds of 1 are undefined. The number of cut points should be c minus 1, since each cut point represents a threshold between consecutive cumulative probabilities. We'll see this concretely in the example coming up. The simple cumulative logit model only had cut points. The proportional odds model extends it by bringing in explanatory variables. Here's the simple cumulative logit model we just built, with nothing but a cut point on the right-hand side. The proportional odds model adds the linear predictor xi transpose beta to it. The cut point alpha j shifts with the category, but the coefficient vector beta is shared across every cut point. That shared beta is exactly what gives the model its name. Following from the definition of the odds ratio, if the kth explanatory variable is continuous, then the log odds ratio from the proportional odds model is given by this expression. Reading that from the bottom up, the denominator is the odds of being in category J or lower. The numerator is the derivative of those same odds with respect to the kth predictor. So beta k is the rate of change of the odds expressed relative to the odds itself. In plain language, the regression coefficient represents the change in the log odds of being in category J or lower for a 1-unit increase in the corresponding predictor. And critically, that same beta applies at every cut point J. The predictor shifts all the cumulative log odds by the same amount, which is the proportional odds assumption. Let's see it in action with an example. Consider a study examining the effect of age on the likelihood of developing lung cancer. The outcome variable is ordinal with 3 categories: no cancer, early stage cancer, and advanced stage cancer. These are clearly ordered by severity, which is exactly the structure a cumulative model is built for. The proportional odds model here is the cumulative logit of the probability of being in category J or lower given age, equal to the cut point alpha j plus beta age times age. Assume the coefficient for age is 0.05. Exponentiating gives an odds ratio of e to the 0.05, which is approximately 1.051. An odds ratio above 1 means age is positively associated with the cumulative categories. For each additional year of age, the odds increase by about 5.1%. For j equals 1, the odds of remaining in the no cancer category versus moving to a more severe category increase by 5.1% per year of age. For j equals 2, the odds of being in early stage or no cancer versus advanced stage increase by the same 5.1%. And for j equals 3, since this is the highest category, it encompasses everything below it. The probability is always 1, so we don't interpret a logit for it separately. This is why we have 2 cut points, not 3. Now let's put in numbers. Assume alpha 1 is -1, alpha 2 is 1, and we're looking at a 40-year-old. For the first cumulative logit, we take alpha 1, -1, plus 0.05 times 40, which is 2. -1 plus 2 gives us 1. Converting that logit back to a probability, we take e to the 1 over 1 plus e to the 1, which is about 0.731. So based on this model, a 40-year-old has a 73.1% chance of being in the no cancer category. For the second cumulative logit, the only thing that changes is the cut point. Alpha 2 is 1, plus the same 2 from the age term gives 3. That converts to e cubed over 1 plus e cubed, which is about 0.953. So a 40-year-old has a 95.3% chance of being in either the early stage or the no cancer category. And because the cumulative probabilities have to reach 1 at the top category, we can back out the last one by subtraction. 100% minus 95.3% leaves 4.7%. So a 40-year-old has a 4.7% chance of being in the advanced stage cancer category. Just as the logit model had a probit counterpart in the binary case, the cumulative logit model has a cumulative probit counterpart. Instead of the logistic function, it uses the standard normal distribution. The cumulative probit model says the probability of being in category J or lower equals the standard normal CDF evaluated at alpha j minus xi transpose beta. Here, phi is the standard normal cumulative distribution function. The star variable, yi star, is a latent variable. It's an unobserved, continuous variable that underlies the observed ordinal outcome. The same idea as the threshold model we saw with the binary probit. It's modeled as a linear function of the explanatory variables plus a normally distributed error term. We never observe it directly. What we observe is which interval it lands in. Picture the latent variables distribution as this bell curve. Every observation sits somewhere along this continuous scale. The cut points alpha 1 and alpha 2 slice that continuous scale into ordered intervals. If the latent variable falls below alpha 1, we observe category 1. If it falls between alpha 1 and alpha 2, we observe category 2. and if it falls above alpha 2, we observe category 3. Writing that out in general, y equals 1 if the latent variable is at or below alpha 1, 2 if it's between alpha 1 and alpha 2, and so on, up to category C if the latent variable exceeds alpha C minus 1. This is the whole idea behind the cumulative Probit model. The latent variable partitions a continuous scale into ordered categories, which lets the model capture the ordinal nature of the response. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.